Okay, bit of an experiment here. Lighting, could use a little more light for a video, but we'll see. I ran out of time last night at home to make the velocity versus time graph video for Physics 11H, or Physics H, so here we go. A little bit on velocity versus time graph. I've got these special markers that are a little bit larger. Hopefully it'll translate into the video. So we've looked at position versus time graphs. How's that one? See it? That axis isn't so great. Alright, gotta be careful how I write here. Position versus time graph. Symbol we use is an X and a T. Seconds. X is in meters for position. So if something was walking at a nice constant rate, right? Boom, boom, boom. So the dot represents the person walking to the right, nice constant positive velocity. So we'll say that's the zero location. It's our coordinate system positive. Now, all right. Its position versus time graph would be nice and linear. Right? Nice linear, nice straight line. Every second, right, it's going the same distance forward. All right, every second it's going the same distance forward. So 1 second, it's gone a certain distance here. Another second, certain distance here. So on. Put a fit line in there, and that's what it would look like. So we're going to see in lab how we generate a position versus time graph is we plot something's location. First, we just write it down on a data table. Plot something's location as a function of time, where it was at what time. We'll do that in lab today, hopefully outside here. All right, so velocity versus time, or you may have already done that, and now you're watching the video. Velocity versus time, it tracks how fast something is going as a function of time. Now, these two graphs are related, position versus time and velocity versus time, but I draw their axes. Velocity is going to be in meters per second. I draw their axes a little bit different, right? Because we got to keep track of negative velocities to go along with this, right? And positive velocities. So we've already said the slope of a position versus time graph tells us the velocity of the object. All right, so the slope, you use your slopometer, right? This is the special large dry erase marker. So the slope of this line tells me what's going on with the velocity. Since I have a nice positive constant slope of my position versus time graph, I have a nice constant positive velocity. So this line would actually be flat. So if I have a velocity versus time graph, right, I have some sort of velocity scale, I know what's moving. So let's say that velocity corresponds to 7.5 meters per second. I'm just making that up, all right? So at 1 second, at 0 seconds, it was going 7.5 meters per second already. And at 1 second, it's still going 7.5 meters per second. 2 seconds, 3 seconds, 4 seconds. Every time, it's moving at 7.5 meters per second. Don't ever put arrows on your lines, right? We don't know what happens beyond the time scale we're given. So don't say here. Remember, these graphs are actually produced by plotting individual points and then applying fit lines, best fits, curves or lines of best fit. So there we go. Let me just give you another little quick example here. Oh, this is the lousy eraser. I have to just deal with it. But this special dry erase marker does seem to erase pretty well. So there we go. Let's say we have something moving and stops. Velocity versus time graph. Something moving then stops. I can't remember if this is one of the homework problems or not. V and T. When we're just doing qualitative graphs, we often don't put the units on the scales because it's assumed, right? So hopefully this marker is showing up good enough in the video. Guess I'll see when I upload it. V and T. So it's moving, let's say it's moving in the positive direction. Actually, you know what? Let's have it move in the negative direction. Let's say it's moving to the left, what we call the negative direction. So motion map, right, starts at 0, and actually let's say it moves to the left. And it stops. Right? So it actually would be negative constant velocity, and whatever time it stops at, the velocity would actually go down to 0. I usually connect these vertical lines, although I guess that's not really mathematically accurate, but that's the way we usually sketch it. So we have a negative constant velocity because it's moving to the left for the time, and then stops and it halts. All right, that should be enough to get you going on velocity versus time graphs. It's showing the velocity of the object as it moves. It doesn't show the literal motion. Whether or not the velocity is positive or negative means the direction of motion. Okay, so a negative velocity means it's moving backwards. A positive velocity is moving forwards. All right, so take a look at this. It'll be in the constant velocity topic. One thing you might say, that's not a constant velocity because it changed, right? Well, what we mean by constant velocity is that it's flat. The line is flat. It can change values, but it's not changing as it moves. It doesn't have a slope. Velocity versus time is flat. That's what we mean by constant velocity. Okay. All right. Have a good one.